Assalamualaikum and a very good day everyone. So today, me and my group will present on radioactive substance in the environment. So according to the International Atomic Energy Agency or IAEA 2022, radioactive substances are materials that contain unstable atomic nuclei. So before these nuclei are unstable, they naturally release energy in the form of ionizing radiation, namely alpha, beta, and gamma radiation to become more stable. So radioactive substances exist naturally in our environment, such as rocks, soil, and even certain food. So they can also be produced through human activities like nuclear power generation and medical treatment. So these are 4 common radioactive substances that are widely used or commonly discussed in environmental science. So the first one is uranium. So uranium is a naturally occurring radioactive element found in rocks and soil. So it is actually best known as the main fuel used in nuclear power plants. So during nuclear fission, uranium atoms split and release enormous amount of energy, which is converted into electricity. So according to IAEA, around 10% of the world electricity is generated using nuclear energy. So next one is radium. So radium is produced naturally from the decay of uranium. It emits strong alpha, beta, and gamma radiation. So historically, radium was used in luminous watch and cancer treatment. However, scientists later discovered that prolonged exposure caused serious health problems. So its use is now highly restricted. So the third example is cesium-137. So unlike uranium and radium, cesium-137 is actually artificial, meaning it is produced during nuclear fission inside nuclear reactor. So it became well known after the Chernobyl and Fukushima nuclear disaster because large amounts were released into the environment. So one concern with cesium-137 is its 30-year of half-life, allowing it to remain in soil for decades and enter the food chain. So lastly is iodine-131. Iodine-131 is actually an artificial radioactive isotope and is one of the most important radioisotope that is used in medicine. So it is used specifically to diagnose and treat thyroid disease because our thyroid gland actually absorbs iodine. So this makes iodine-131 highly effective in destroying abnormal thyroid cells while minimizing damage on other cells. Okay, so now let's discuss where radioactive substance come from. So radioactive substance actually originate from 2 major sources, which is natural source and artificial source. So let's begin with natural sources. So the first natural source is cosmic radiation. So high energy radiation continuously reach Earth from outer space. Fortunately, our atmosphere absorbs most of it, protecting living organisms inside the Earth. So secondly, rocks and soil naturally contain radioactive elements such as uranium and radium. So as these elements decay, they produce another radioactive substance known as radon gas. So radon is actually a particularly very important because it is colorless, odorless, and can accumulate inside building. So according to WHO, radon is actually the second leading cause of lung cancer after smoking. So natural radionuclides are also present in food and drinking water. For example, bananas contain potassium-40, which is naturally radioactive, but the radiation level is extremely low and does not pose health risks. Now let's move on to artificial sources. So this includes nuclear power plants, hospital using radioisotope for diagnosis and treatment, industrial applications such as sterilization and leak detection, and nuclear weapons testing or nuclear accidents. So these human activities can actually release radioactive materials into the environment if proper safety measures are not followed. So even though radiation is often viewed negatively, radioactive actually have many beneficial applications. So the first application is in medicine. So according to WHO, radioactive isotopes are widely used in nuclear medicine to diagnose disease and treat cancers. So for example, iodine-131 is used to treat thyroid cancer, while PET scans use radioactive traces to detect abnormalities inside the body. So the second application is energy production. So nuclear power plants use uranium to generate electricity without producing greenhouse gases during operation. So this makes nuclear energy an important low-carbon energy source, although radioactive waste must be carefully managed. So third application is in industry. So radioactive isotope actually help detect leaks in underground pipelines, sterilize medical equipment, and inspect the quality of manufactured products without damaging them. So another important application is in agriculture. So food irradiation uses controlled radiation to destroy bacteria, parasite, and insect, helping food last longer while improving food safety. So radioactive techniques are also used for pest control through the sterile insect technique. So finally, radioactive substances are essential in scientific research where radioactive traces help scientists understand biological processes, environmental pollution, and chemical reaction. Therefore, radioactive substances are valuable tools that greatly improve our quality of life when used responsibly.
Fate of radioactive. After radioactive substances are released into the environment, they do not stay in a place, as this being supported by Volcanic 2019. In his publication, these radioactive substances can spread through air, water, and soil through natural occurrence, cosmic radiation, and also human activities, which allow the contamination to reach to the surrounding areas. And over time, these substances can settle in soil or sediments where it will remain for a certain period of time. The length of time these substances can remain uh, depends on their half-life, which is the time required for half of the radioactive atoms to decay. So this half-life varies greatly among different radioactive substances. For example, in our case, for the iodine 131 has a very short half-life, which is about 8 days. So it decays relatively quick. In contrast, for the cesium 137, it remains radioactive for about 30 years, while for the radium and uranium have a much longer half-life, and it can persist in the environment even longer for thousands to billions of years. So all these substances can also be transported over long distances by wind or flowing water. For wind, it can carry radioactive gas through the atmosphere, while river and groundwater can spread contamination far from the original release site. That's it.
For the uses of radioactive materials, first and most importantly is medicine. In nuclear medicine, doctors use tiny, safe amounts of short-lived radioactive traces like technetium-99M to travel through a patient's body and create highly detailed images of organs and bones. On the treatment side, we use high-energy radiation to target, shrink, and destroy cancer cells during radiotherapy. Beyond hospital, industry relies heavily on this technology. Engineers use gamma ray radiography to scan inside massive metal structures, welds, and pipelines. It acts like an industrial X-ray, letting us find hidden cracks before a structure fails without having to tear it apart. We also see its impact in energy production, where the fission of uranium 235 provides massive amount of low-carbon electricity globally. And finally, in agriculture, controlled radiation is used to irradiate food, killing harmful bacteria and pests so our food stays safer and lasts longer on store shelf. So, for the health effects of radioactive, it helps to split into two categories: immediate effects from high doses and long-term effects from low doses. If a person is exposed to a very high dose of radiation in a short period, which generally only happens during severe nuclear accidents or industrial mishaps, it causes what we call acute radiation syndrome or ARS. The immediate symptoms are swift and harsh: intense nausea, vomiting, diarrhea, and severe skin burns that resemble terrible sunburns. On the inside, the radiation destroys fast dividing cells, particularly inside our bone marrow. This cripples the body's ability to produce white blood cells, leaving the immune system completely vulnerable. At extremely high levels of exposure, the damage spreads to the gastrointestinal and central nervous system, which can unfortunately be fatal within days or weeks. Fortunately, those high dose scenarios are incredibly rare. What is more common to study are the long term chronic risks of low dose exposure. To understand this, we have to look at the cellular level. Radiation is ionizing, meaning it has enough energy to knock electrons out of atoms, breaking chemical bonds and directly damaging our DNA. When DNA is damaged, the cell usually repairs itself. But if it repairs itself incorrectly, the cell can start replicating out of control. This is the direct link to cancer, over years or decades. Low-level chronic exposure can significantly increase the risk of developing leukemia, as well as thyroid, lung, or breast cancer. Other long-term effects include cataracts, which is the clouding of the eye lens over time. Because of this risk, the global scientific and industrial community follows a golden rule called ALARA, which stands for as low as reasonably achievable. It means every process, every lab, and every industry must design their workflows to keep radiation exposure as close to zero as possible.
Next, I will discuss two key concepts, which are bioaccumulation and biomagnification. Bioaccumulation is the buildup of substances within a single organism over time. For example, a fish absorbs contaminants faster than it can eliminate them, while biomagnification is when this concentration increases as the organism moves up the food chain. Top predators end up with the highest levels, like mercury in tuna. However, a recent study along China's coastal waters found something different, which is biodilution instead of biomagnification for certain radionuclides. So, let's look at that study. This study was published in Environmental Research 2025, analyzed 304 samples from 16 marine species across 4 Chinese seas. Researchers measured 4 radionuclides, which are polonium-210, strontium-90, cesium-137, and plutonium-239 or 240. They use stable isotope analysis to track movement through the food web. So, what is the key finding? The table 2 shows mollusks had the highest radionuclide level, while fish, which is the top predators, had the lowest. The trophic magnification factor was less than 1 for all radionuclides, confirming that it is biodilution. So, why does this happen? This is because radionuclides are water-loving, so they circulate in fluids and are easily excreted through kidney and gills. As fish grow larger, the contaminants become diluted in their bigger body mass. So, unlike mercury, which biomagnifies, these radionuclides actually dilute up the food chain. So, this shows that each contaminants behave differently.
Now I will explain one of the most serious nuclear accidents in history, the Chernobyl disaster. The Chernobyl disaster occurred on 26 April 1986 at reactor number 4 of the Chernobyl nuclear power plant, located near the city of Pripyat in present-day Ukraine. It is widely regarded as the worst nuclear power plant accident ever recorded. For the background, the accident happened during a late-night safety test. The purpose of the test was to determine whether the turbines could continue supplying electricity to the cooling pump during a power outage before the emergency generator started. Unfortunately, the operators made several mistakes while carrying out the test, and the reactor itself had significant design flaws. This factor combined to create an uncontrollable power surge that caused 2 explosions and a graphite fire. The fire burned for several days, releasing large amounts of radioactive and materials into the atmosphere. For the radioactive material release, several radioactive isotopes were released during the accident. The most significant were iodine-131, cesium-137, strontium-90, and a small amount of plutonium isotope. Each isotope affects the human body differently. For example, iodine-131 accumulates in the thyroid gland and greatly increases the risk of thyroid cancer, especially in children. Cesium-137 remains in the environment for decades, while strontium-90 behaves similarly to calcium and accumulates in bones. Plutonium is highly toxic if inhaled, although its contamination remains mostly close to the reactor. Next, environmental fate. After the explosion, radioactive particles were carried by wind across Ukraine, Belarus, Russia, and many other European countries. This radioactive substance contaminated forests, rivers, lakes, farmland, and urban areas. Because some radionuclides have very long half-life, contamination has persisted over decades. To reduce human exposure, authorities established a 30-kilometer exclusion zone around the power plant, where people still prohibited from living permanently.
Human health effect. The health impacts were both immediate and long-term. Immediately after the explosion, 2 workers died and 28 emergency respondents later died from acute radiation syndrome or ARS after receiving extremely high doses of radiation. Over the following years, thousands of thyroid cancer cases were reported, particularly among children exposed to radioactive iodine. Researchers also observed increased risk of leukemia, cataracts, cardiovascular disease, and physiological disorder among the affected population. For environmental impact, the surrounding environment was severely damaged. A nearby forest turned reddish-brown after exposure to intense radiation and became known as the Red Forest. Large areas of farmland became unsuitable for agriculture and many wildlife populations were initially affected. Today, although some wildfire had returned, radioactive contamination remains in soil and vegetation, requiring continuous environmental monitoring. For the conclusion, the Chernobyl disaster taught the world many important lessons. It highlighted the need for safer reactor design, stricter operating procedure, better emergency preparedness, and greater transparency in reporting nuclear accidents. These improvements have significantly strengthened international nuclear safety standards. Now, let's move to the second case study, the Fukushima Daiichi nuclear disaster. The disaster occurred on 11 March 2011 at the Fukushima Daiichi nuclear power plant in Japan, following the devastating Great East Japan earthquake and tsunami. It is classified as a Level 7 nuclear accident, the highest level on the International Nuclear and Radiological Event Scale. For the background, unlike Chernobyl, Fukushima was not caused by human error but by a natural disaster. A magnitude 9.0 earthquake struck off the coast of Japan, generating a tsunami over 13 to 50 meters high. The tsunami flooded the nuclear power plant and disabled its emergency diesel generator. Without electricity, the cooling system stopped working, causing 3 reactor cores to overheat and melt. Hydrogen gas accumulated inside the reactor buildings, leading to several explosions. For radioactive material release, the main radioactive substances released were iodine-131, cesium-134, and cesium-137. Although the release was significant, it was much lower than that of Chernobyl because Japanese authorities acted quickly to cool the reactor and limit the further emission. For the environmental fate, radioactive material contaminated nearby land, forests, and agriculture areas. In addition, some contaminated water entered the Pacific Ocean. Groundwater surrounding the plant also became contaminated and has required continuous treatment and monitoring. Japan continues to conduct long-term environmental surveillance to ensure radiation levels remain safe. Next, human health effect. Unlike Chernobyl, no deaths were directly caused by radiation exposure. However, many workers received increased radiation doses while stabilizing the reactor. The evacuation of nearby communities also caused significant physiological stress, anxiety, depression, and health problems, especially among elderly residents. Studies suggest that the long-term increase in cancer risk for the general public is expected to be relatively low. For environmental impact, large areas surrounding the plant requires extensive decontamination. Fishing activities near Fukushima were temporarily restricted because of radioactive contamination in coastal water. The Japanese government has spent many years removing contaminated soil, cleaning affected communities, and managing radioactive wastewater generated during the cooling process. For the lesson learned, the Fukushima disaster demonstrated the importance of preparing nuclear power plants for extreme natural disaster. It also emphasized the need for a stronger flood protection, more reliable backup power system, continuous radiation monitoring, and well-planned emergency evacuation procedure. Many countries have since reviewed and strengthened their nuclear safety regulation based on the lesson learned from the Fukushima tragedy. For the conclusion, both the Chernobyl and Fukushima disaster had major environmental, health, and social impacts. Although they occurred under very different circumstances, this event reminds us that while nuclear energy is an efficient source of electricity, it requires strict safety standards, continuous monitoring, responsible management, and effective emergency preparedness to protect both people and the environment. Next, I will explain the methods used to monitor radioactive substances. Monitoring radioactive substances is very important because it helps detect radiation early, measure exposure level, prevent contamination, and ensure the safety of workers, the public, and the environment. Several monitoring techniques are used depending on the type of radioactive material and where it is being handled. The first method is the gigamolar or GM counter. This portable instrument detects alpha, beta, and gamma radiation. It is commonly used to check work surfaces, laboratory equipment, clothing, and surrounding areas for radioactive contamination. If a spill occurs, the GM counter can quickly identify contaminated areas so that they can be cleaned safely. The second method is the personal dosimeter. A dosimeter is worn by workers who regularly handle radioactive material. It measures the total amount of radiation a person receives over time. This ensures that workers do not exceed the recommended radiation exposure limits and help protect their long-term health. The third method is the scintillation detector. This detector is more sensitive than a GM counter and especially effective for detecting gamma radiation. It is widely used for environmental monitoring, such as measuring radioactive contamination in soil, water, and around nuclear facilities. It is particularly useful for monitoring radionuclides like cesium-137. I will explain the method of handling radioactive material and the safety measure for 4 common radioactive substances: uranium, radium, cesium-137, and iodine-131. First is uranium. Uranium should be stored in sealed containers and handled in a well-ventilated area or glove box to prevent radioactive dust from spreading. When handling uranium, workers should wear gloves, a lab coat, and a mask to avoid inhaling or swallowing uranium dust. Washing hands after handling is also important to prevent contamination. The second substance is radium. Radium should be stored in lead-lined containers and handled using forceps or remote tools to reduce direct contact. Safety measures include wearing personal protective equipment, using lead shielding to block radiation, wearing a personal dosimeter to monitor exposure, and limiting the amount of time spent near the source. Next is cesium-137. It should be stored in lead or concrete containers and handled remotely whenever possible. Workers should wear a dosimeter, use thick lead shielding, maintain a safe distance from the source, and minimize the time spent handling the material to reduce radiation exposure. Lastly, iodine-131 should be stored in lead containers and handled inside a fume hood because it can easily become airborne. Safety measures include wearing gloves, a lab coat, and a dosimeter, avoiding inhalation of iodine vapor, and monitoring the thyroid gland for workers who are regularly exposed. In summary, each radioactive substance requires specific handling method and safety precautions. However, the main goal is always the same: to minimize radiation exposure, prevent contamination, and protect both workers and the environment.
So to sum things up, radioactive substances are unstable material that naturally emit ionizing radiation to become more stable. So today we learned about their definition, common examples, sources, beneficial applications, study case, and many more. So according to IAEA, radioactive substances have transformed medicine, energy production, agriculture, industry, and scientific research. However, historical disasters such as Chernobyl and Fukushima remind us that improper management can lead to severe environmental contamination and long-term health effects. So therefore, continuous environmental monitoring, strict safety regulation, and responsible handling are essential to ensure that radioactive substances remain within acceptable level and continue benefiting society while protecting both human health and the environment. That's all from us. Thank you.